Okay, hello everybody. So, got bored today, decided to do another video in the morning. So here we are. So this video, the purpose of it is to figure out the structure of the compound that gives the following mass spectrum, FTIR, and proton NMR. So I'm gonna try to go through how I usually think about these problems, and then we'll see how it goes. Okay, so basically, this is the order in which you see it is not necessarily the order you'll always see these spectrum. Order doesn't really matter, but I usually like to work my way from the mass spectrum to the IR to the proton NMR. But that's up to your preference. If you've been practicing a different way, do your way, but this is just how I find the most, this is the most logical way for me to tackle the problem. So the first thing that you're going to do in your mass spectrum is you're going to look at your molecular ion peak, right? And so the molecular ion peak here is, and you have to be careful because you have to make sure you count these carefully enough so that you get the exact mass, because even if it's off by one mass unit, that would make so much difference. So here it's 110, 11, 12, 13, 14. So the mass spec, the molecular weight of our compound is 114 grams per mole, technically. Okay, so that's good. So what does that mean? Okay, 114 now. From that, I can kind of get a few possible um, molecular formulas. So if I take 114, right? Let's say I'm gonna ballpark it. Let's say, what if I have 9 carbons in my compound? Well, if I have 9 carbons in my compound, then that would mean that that would give me a mass of 108, right? And that would leave me with about 6 hydrogens so that I could get to 114. Now that doesn't make sense, right? A C9H6 molecular formula, that doesn't make sense. So we're scratching that. Okay? Um, Let me just erase that then. Okay. Now, what else is possible? Well, okay, let me try to ballpark it again. I'm going to go a little bit less this time. Um, let's say 8 carbons, right? So if I have 8 carbons, that would give me a molecular weight of 8 times 12. Gotta think about it a little bit. That's 96, right? 12 times 5 is 60. Yeah, 96. And then that leaves me with about 18 mass units to play with. So I could say I have 18 hydrogens, right? And that would give me 114. So one possible molecular formula is C8H18, right? That's one possible molecular formula. Let me actually just write it somewhere else really quickly right now. So C8H18 is one possible molecular formula. Let's try another one. Okay, what if I try, because there could be multiple ones, right? So you don't want to just try one and say, okay, this one works, let me go with that. Let me try another one. What about 7 carbons? 7 carbons should give me a molecular weight of 84 mass units. And then let's say I have 7 carbons, and I just want to look at my notes here. Okay, 84, the difference between 84 and 114 is about 30 mass units, which is too many hydrogens. So in this case, what I would do is I'd say, okay, I have 1 oxygen, that gives me 16, and then I have 14 hydrogens, which is 14, and that gets me to 114 as well. So another possible molecular weight is C7H14O, right? Now I'm just going to work with these two possible formulas for now. So I'm going to erase the rest of this. Okay. And I'm going to start again. Okay, so now given that I have two possible molecular formulas, I could go with calculating the unsaturated, the degrees of unsaturation, right? And the formula for that, if you remember, is 2 carbons plus 2 plus how many nitrogens minus the number of halogens minus the number of hydrogens all over 2. Right? Now remember, the reason why we said there wasn't any nitrogens in this is because I didn't mention this earlier, but I should have. The only way, if I had a nitrogen, then my molecular weight would be an odd number, right? Nitrogen gives odd mass to charge ratio, right? If I had one nitrogen, that is. If I had two nitrogens, it would be even and it would be harder to elucidate, and that could be a possibility here. I don't want to go down that rabbit hole, and that's the key to these problems. There's so many rabbit holes that you could go that you could follow, and you have to be careful. You have to follow your instinct. You have to follow your heart in a way, right? So let me calculate the degrees of unsaturation for these guys. So the degrees of unsaturation for this guy is going to be equal to 2 times 8 plus, right, let's put that in brackets, plus 2 minus 18 all over 2, and that is equal to actually 0. So that means there's no double bonds, there's no rings, nothing, right? Now what about this molecular formula? Okay, well, if I do it here, then that would be 2 times 7 plus 2 minus 14 all over 2, because oxygen really doesn't play a role when you're calculating degrees of unsaturation. That actually gives you 1, right? Because 14 plus 2 is 16, 16 minus 14 is 2, 2 divided by 2 is 1. So that means I have
but
either...
I usually just do the full screen and then cut it down to size
I have either
later. So let's do that.
A ring or a double one in this case, right? I don't know which one is, whether I have a ring or a double one. All I know is I have one of them. Okay, so I'm just going to delete this just for space. And I'm going to say here, okay, I have 0 degrees of unsaturation and 1 degree of unsaturation here, right? Okay, now you could go ahead and look a little bit more in depth into the mass spectrum at this point, right? You could look at the possible fragments that you're forming, but that's a rabbit hole that I choose not to follow. At this point, I'm ready to move on to my IR spectrum, right? Now, when I look at my IR, the first thing that's going to be screaming at me, right, is this fella here. This tells you so much. This is probably one of the most useful informations that you could get, right? Now this this peak here, if we look at it, is around 1700 wave numbers, right? What does that tell me? That tells me that I have a double bond O. I have a carbonyl, right? And that's so important. That's so much information that you get from just that one peak. Why? Because if I have a C double bond O, that means I have to have an oxygen in my molecular weight, which means that this formula here, that doesn't work anymore, right? Not only that, but that means that this 1 degree of unsaturation is actually from the C double bond O. So that resolves that, right? So at this point, what I usually do is I start kind of compiling the list, right? Kind of a list of criterias. List of, or requirements, let's say, I don't know. Whatever you want to call it, that doesn't matter. So I know 1, my molecular weight is C7H14O. That's number 1, right? Number 2, I have to have a C double bond O, right? And from the molecular weight, you could get that that's 1 degree of unsaturation. Number 2, I have to have a C double bond O, right? In my IR, in my molecule, sorry. So let me look again at the IR. Well, okay, I see here that there's a peak at around 30,000. That just means you have an SP3CH. Nothing special. It is useful information, but I mean that was somewhat assumed because we only had 1 degree of unsaturation and we had 14 hydrogens, right? It's pretty. Usually the region that I look at is somewhat here and anything below 3,000, right? Honestly, from this IR at this point is there's not much information to gain from it anymore because the rest of the peaks obviously are in the fingerprint region. We don't want to go into that mess, so I'm gonna now move on into my NMR. Now, when I look at my NMR, what do I see? And by the way, I forgot to mention, all of these spectrum that I'm showing you right now, they're actually spectrum of the actual molecule. They were actually taken. They're not theoretical spectra. So that's why it looks really bad when you look at the NMR. You can't really distinguish between a triplet and a doublet and a singlet because this is an actual real spectrum, right? I'll tell you here, this is a triplet. This is a multiplet, and this is also a triplet, and this is 3 integration, this is 2, and this is 2. Just because I already know what the compound is. But you could also see that. I mean, you could see the triplet, right? You could see that obviously this is more than one peak, and it seems like the second peak is at the half point, so that and there only seems to be 2 other peaks, so you can tell it's a triplet, right? This is kind of a mess, but you can tell it's a multiplet. But anyways, so that's what I get. So what I see, the first thing that I see, and the next criteria that I'm going to add here is I have 3 types of hydrogens because I only have 3 distinct protons, right? Okay, so now I could start making my structure. Okay, so 3 types of hydrogens means that there's going to be some symmetry in the compound. There's going to be some carbons that are equivalent, right? So I'm gonna start here. I know for sure I have this, right? I usually don't draw the carbon, and I don't like it when students draw the carbon, right? That's kind of implicit. Okay, so let me try. I'm gonna try some things out here. I'm gonna try 1, 2, 3, 4, 5, 6, 7. I'm gonna try that, right? Problem with this is how many distinct hydrogens do I have? Well, I have 1, right? We're gonna label this as 1. This is 2. This is 3. This is 4, and this is 5. But I only have 3 peaks here, right? So that compound does not work. I'm just going to delete these annotations. Oh, I did not mean to delete that. I'm going to redraw this just so that you guys see that this compound does not work. Right? That doesn't work. Okay. What's another option? Well, I could go ahead and do something maybe kind of like this. Problem is, in this, how many do I have? How many carbons do I have? 1, 2, 3, 4, 5, 6, 7. 7, right? So that follows my molecular formula, and I guarantee you, if you count the number of hydrogens, there'll be 14. But okay, in this case, the problem is how many distinct hydrogens do I have? Well, I actually only have 1. This would only give me 1 peak in my NMR, right? Which would be a doublet in this case because all of these hydrogens are equivalent. There's a line of symmetry that you could draw right there, right? So that does not work. Okay, ooh. I'm running out of options here. Okay, what if I do this guy? How many peaks would I see here? And that's how many, 1, 2, 3, 4, 5, 6, oh, sorry, I'm missing a carbon. Let's put that carbon there, right? Okay, so how many peaks do I have? Well, I have these guys will be my 1. There's no hydrogens here, so that's actually not gonna be a peak, right? Oops, sorry. Right, because carbons only take 4 bonds. Right, that's going to be my 2, and that's going to be my 3. Okay, well, this might work, right? I got 3, that looks like it's going to work. But wait a second, okay, what is the splitting of these 9 hydrogens, first of all? Because I have one CH3, 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 that's 9 hydrogens, right? What's the splitting of that? Well, the splitting is actually just going to be a singlet. Oops, sorry. Because I don't have, there's nothing there. There's no hydrogens adjacent to these CH3s, right? I don't see a singlet here. Also, given that this represents 9 hydrogens, I don't see an integration number where it's 9. Now, that's not necessary. If this was 9 hydrogens, right? This could still be this. This could still be 6 hydrogens and 6 hydrogens. That's a possibility, and that would give me an integration of 322 because 966. That ratio ultimately is 322, so that could still work. But the problem is I don't have 6 equivalent hydrogens, right? I have these 9 hydrogens, which will give me a singlet, which I don't see in my spectrum. And I have this second hydrogen, which should give me a quartet, right? And this terminal one should give me a triplet. Well, I do see a triplet, but I don't see a quartet, right? So that just does not work at all. Anyways, okay. Well, what's next? What's another option? Okay, well, what if I do a straight chain and make it symmetrical so that I could get similar integration numbers? Maybe that works. Okay, well, I got 1, right? This is 1, 2, 3, 3, 2, 1, right? Because these carbons are the same, these carbons are the same, and these carbons are the same. Okay, well, these are 3 signals, right? And the terminal carbon has 3. I'm going to do that in a different color just so that it's not confusing to everybody. I'm going to do that in, oops, I'm going to do that in blue. How about that? So this one has 3 hydrogens, this one has 2 hydrogens, this one has 2 hydrogens, right? 3, 2, 2. Well, okay, that works with my ratio. Let me look at the splitting pattern. Well, this terminal, right? This terminal CH3 is next to a CH2, which means that I'll get a triplet from this. Okay, that makes sense. This guy here, this carbon in the middle here, is between a CH3 and a CH2, so that would give me a multiplet, right? Okay, I got a multiplet, and the integration is 2. And then I have a triplet here. This carbon next to the carbonyl is actually adjacent to a CH2, which means I will get a triplet. Okay, well that works, and the integration works because it's 322, and remember, the terminal carbons are equal, the middle carbons are equal, and the carbons adjacent to the carbonyl are the same as well, because I have a line of symmetry here, right? Okay, so that seems like it's working, right? So I'm going to draw this out again. Okay, now what I like to do is, okay, there's nothing left for me to get from the mass spec. I got all of the from the NMR. I got all of the information I can get from the NMR, and it seemed to have confirmed my final product, right? Now I go back to the IR. Okay, the IR shows me a carbonyl. I'm going to use blue in this case, or let's go with yellow. I'm going to use yellow in this case, right? I see the carbonyl. Carbonyl, I see the carbonyl. The sp3ch peak, well, there's a lot of sp3chs, right? Is there anything else? Not really. So IR seems to be working as well. Okay, let me go back to the mass spec. Mass spec, I have 114 grams per mole. The molecular weight of this compound is 114 grams per mole. Well, okay, let me see the base peak. That's always of interest, right? The base peak is 43. Now, and if I looked at this 43 before I looked at any of the IRs or the NMRs, my first instinct would have been, okay, I got an acylium ion, right? Because I know this acylium ion. Let me just draw that. I know that this acylium ion, right? It could resonate. It could give me this very, very, very stable resonance structure here, right? So that is usually why if you see 43 at a base peak, I usually go there straight away. The problem is, if I look at my compound here, that my template compound, I don't. For me to have an acylium ion, that means I need something like this. I need a compound. Sorry, no, that something happened. My bad. I need a compound that looks like this with a terminal CH3, because that's the only way I could see an acylium ion. Now the carbonyl in my proposed compound, there's actually no terminal CH3 attached to the carbonyl, right? So that would lead me to confusion. And if I went deeper into the mass spec and I thought, okay, I definitely have an acylium ion, and I started making my possible compounds, then I would have ended up with the wrong compound, because I would have probably ended up with something like, well, none of these work, but I could have ended up with something maybe like, what if I did 1, 2, 3, 4, 5, 6, 7, right? If I did this, that would have given me an acylium ion, right? Although the NMR wouldn't have worked, but I could have just did the mass spec and the IR and said, oh, I have an acylium ion, it has to be that, right? But that's not the case. Or it could have even been like something like, right? 1, 2, 3, 4, 5, 6, 7. It could have been that, right? But that doesn't work with my NMR as well. Well, let me tell you what that 43 is. That 43 is actually just that, right? Because that is a CH3, which is 15, plus a CH2, which is 14, that means 29, plus another CH2, 14 plus another 29 plus another 14 is equal to 43. So that's what you see. That is what this peak is, right? It's basically, I'm gonna circle this with a different color just so that nobody gets confused. Okay, right? That is what that peak is, and that is why I don't go too much into the mass spec. I get the molecular weight, I get the molecular formula, or the possible molecular formulas, and the degrees of unsaturation for each molecular formula. And then I go to the IR, and I eliminate any molecular formulas that does not work with my IR. And then I go to the NMR to get the carbon backbone. So that's how I would do it, right? So I hope this video was helpful. If it was, make sure to subscribe to my channel, like the video, and also send an email if you have any questions that you would like answered on this channel. I hope everybody's safe. I guess I'm gonna end with this every time I end a video. Make sure you stay at home unless it's absolutely necessary. Wash your hands and stay 2 meters away or 6 feet away from as many people as you can. Stay safe. Good night.